Hello everyone. Today I'm going to present Tribo-piezoelectricity in bilayers of the two-dimensional materials. Yeah, and the one thing that I will mention here, the two-dimensional materials that are indicated the group 3 nitride monolayers. So they have their monolayers in the hexagonal shapes in the honeycomb lattice, and we will make bilayer with them, and we'll predict tribo-piezoelectricity using these bilayers. And first of all, I would like to discuss about piezoelectricity. So, piezoelectricity is the electric charges that accumulate in certain solid materials in response to applied mechanical stress. And also the type of piezoelectricity is a charge of electricity generated by friction. And what is nanogenerator? A nanogenerator is a type of technology that converts mechanical or thermal energy as produced by a small-scale physical change into electricity. A nanogenerator has three typical approaches: piezoelectric, piezoelectric, triboelectric, electric, and pyroelectric nanogenerators. Both the type of both the piezoelectric and the triboelectric nanogenerators can convert mechanical energy into electricity. However, pyroelectric nanogenerators can be used to harvest thermal energy from a time-dependent temperature fluctuations. So here we're going to consider a bilayer, and we will try to model. We will model a nanogenerator using the group 3 nitride bilayers. And what is why this is? This is because the high electronegativity between the atoms of the two-dimensional group 3 nitrides make them attractive to demonstrating a strong outer plane piezoelectric effect. In the energy harvesting devices can be predicted by calculating the salient piezoelectric features. In plane interlayer sliding between two monolayers leads to a noticeable rise of vertical piezoelectricity. The vertical resistance between the bilayer renders tribological energy by the sliding effect. The structure can be used as a piezoelectric transducer to extract force and stress from the generated out of plane triboelectric energy. So this is we're gonna make the bilayers now. So the bilayers is like we'll stack one layer above another layer. So there will be two layers, the top layer and the bottom layer, and depending on how we stack, there are significant three configurations that I'm going to show you. The AA configuration here, say the group 3 atom is the comparatively bigger atom, and the nitrogen atom is comparatively smaller atom. So in AA stacking is just we have the group 3 atom above the group 3 atom, and the nitrogen atom just above the nitrogen atom. Let's discuss about the every configuration. So every configuration is like that. So the hexagons are produced. So in the bottom there will be nitrogen atom, the center of the hexagon, but at above the top, the group 3 atoms will be at the center of the hexagon. So this is the every configuration, and AC configuration, just if we flip the every configuration will get the AC configuration. So what is the top layer for AC configuration will be bottom layer for AC configuration, and what is the bottom layer for AC configuration will be top layer for AC configuration. So these are the three configurations that is important to discuss. Tribo-piezoelectricity in the bilayers, and now we're gonna discuss about potential energy surface. The potential energy surface is how we find it is like we'll keep the bottom layer fixed, and we'll translate the top layer in different XY positions, and we will record the energy change, and as well as the polarization deviation change. So first, the energy change that is we're gonna refer as potential energy surface. So first, the interlayer distance when it is 2.8 for Armstrong, say. So when the top layer it slides with respect to the bottom layer, it goes to different configurations like AA configuration, AC, and AB configuration, and it's the potential energy changes. So the maximum is 7 755 milli electron volt potential energy we get for A configuration, and the minimum is somewhat in AC or AB configuration. However, when we compress it more to get a reduced interlayer distance of 2.5 1 Armstrong, the potential energy difference is even increases. So for first side it was 755 electron volt, but here we are getting 1230 electron volt. So it's much more increased. So when you compress it, we're gonna have more potential energy difference. And the polarization deviation surface is we see that the polarization deviation as shown in two different interlayer distances. The first one is 2.81 Armstrong, and the second one is 2.51 Armstrong. So for the first interlayer distance, we're going to see that the maximum polarization deviation we're going to find is 4.5 picocoulomb per meter square. This type of square wave. So, and when we reduce it to 2.5 on Armstrong, the interlayer distance is significantly increased to 11.5 picocoulomb per meter square. And if we notice the colors here, that the red is the maximum, while the blue is the minimum. So the maximum occurs at A configuration, and the blue is for, I think it's the AB is the AB configuration. That is not pointed here, but it would be the AB configuration. So for AB configuration, we are getting the lowest polarization difference. So our starting point can be AB configuration, and we will gradually go to A configuration while during the interlayer sliding process. And this is the energy correlation. That is the difference of maximum energy minus what we get the lowest energy. And this is something that energy correlation is very important when we model the nano generator and predict how much electricity it's going to produce. So this is the curve of energy. This is the curve of polarization deviation with respect to the energy correlation. So it shows somewhat linear increase. So as much as the energy correlation increases, the polarization deviation also increases also similar amount, and we're going to see the charge density difference variation. So if you notice that it is for AB configuration, and this is for an interlayer distance of 2.81 Armstrong, and this is for the bottom one in the lower section is for 2.51 Armstrong. So if we compare these two figures, we can see that from the above figure to the lower figure, you can see that the charge density difference has been increased significantly. So if we compress it and the interlayer distance is reduced, so the charge density difference is gradually increases. So in the next slide, it's gonna show that a comparison how is accumulated in the top layer with respect to the bottom layer. I will see that whatever the AB configurations or in AC configuration, the top layer getting the more pairs compared to the bottom layer, and it is somewhat better for A configuration here. The difference between charge difference between the top layer and bottom layer is even more, and gradually the more we decrease the interlayer distance, that is we compress the spallier structure, the top layer gets more charges. So this is we can see that for A configuration, when you compress it, there is the top layer get more charges compared to the bottom layer, and so there gets a potential difference. And if we put a voltmeter between the two layers, we'll get a voltage difference. The same is here, that the charge gain in the top layer is much more better than the bottom layer, so there will be potential difference. And this is in the next slide we calculated the potential difference of the top layer with respect to the bottom layer. So here is the 2.8 Armstrong, where the potential electric potential difference between the two layers is somewhat like 0.15 electron volt. That if you gradually compress it and the interlayer distance is reduced to somewhat like 2.4 Armstrong, we're going to get a potential energy difference of around 0.2 electron volt. So the more we compress it, the more we're going to get potential energy difference, electric potential difference between the two layers, and we're going to get the electricity, and that we're gonna model our nano generators as well as energy harvesting devices for daily applications. And the next slide is about a schematic diagram of how we're gonna model the nano generator. Here he said this is our top layer, this is the bottom layer. the green, these are the gold anodes that we used, and this is our probe. So whatever we compensate when we slide it gradually, it's gonna give us electricity, and it's very compromising in our present energy situation. If it's and we hope that it's gonna get into experimental realization, and we will use it in our daily life as to meet our present energy crisis. Thank you, everyone, and I hope to see you next.